What's up, geometry? Thanks so much for tuning in for another episode of Math with Mullins. Today we're going to be looking at lesson 2.2, inductive and deductive reasoning, and our main goal is just to figure out how we can use them. The first thing we want to talk about are two separate types of vocabulary terms. The first one is called a conjecture, and that's an unproven statement that is based on observation. So if you just observe something, say like, I observed that you've gotten an A on a quiz, I think that you know this material really well. Well, you could know the material really well, or you could have just gotten lucky and when you took the quiz, okay? Inductive reasoning, though, is when you find a pattern in specific cases. So we're going to look at inductive reasoning can help you write a conjecture based on the patterns that you're seeing. So the first three or four questions are asking you to look at different figures and find and establish patterns. So that's exactly what we're going to talk about here. A conjecture would just be making a statement about what the figure could be, but the inductive reasoning is when we find that pattern. So if we were to draw the fifth figure in the pattern, for example, 1, it would look like this. So we have figures 1, 2, 3, and 4. Notice how, and I didn't draw a big figure 4 here, but figure 4 would have a circle, and then you would have 8 sections. So 1, 2, 3, 4, 5, 6, 7, 8 with this first one drawn, but now this figure has 10 sections, okay? So we're just adding 2 sections each time and coloring in that first section for each one, okay? The same thing would be here for number 2. The next figure in the pattern would just be a star, and we're going to shade in the middle portion and only the bottom left leg. For number 3, we start with 1 circle, then we end up with 3. Now we're going up to 6. So we're adding on like a level each time. So this level has 4 circles, then 3, then 2, then 1. Okay. So those are about dealing with patterns. Now let's look at this exact conjecture. Numbers such as 3, 4, and 5 are called consecutive integers. So make and test a conjecture about the sum of any 3 consecutive integers. So the sum meaning we would add them. So we would first want to establish a pattern. Okay, so we can start with 3, 4, and 5. 3 plus 4 plus 5 is equal to 12. Okay, and maybe we try 7 plus 8 plus 9. 7 plus 8 plus 9 would be 24. Okay, and then maybe we would also try another one like 13, 14, and 15, and that is equal to 42. So what I've tried to do is establish a pattern of adding consecutive integers. What I'm noticing, though, is each of these 3 integers have a factor in common. They both can be multiplied by 3. So like 12 can be 3 times 4. 24 could be 3 times 8. 42 could be 3 times 14. So the conjecture that I would make would be the sum of any 3 consecutive integers is 3 times the second number. So you see how 3, 4, and 5, I did 3 times 4 gives me 12. 7, 8, and 9, 8 times 3 gives me 24. 13, 14, 15, 3 times 14 gives me 42. Okay, so when we test it, that's what we also want to do is maybe we do like 50 plus 51 plus 52. That added together is 153. Well, is 3 times 51 equal to 153? Yes. Okay, you can even do this with, we forgot to do some negatives, but let's say we do negative 5 plus negative 4 plus negative 3. That'll give us negative 12. And like before, is 3 times negative 4 equal to negative 12? Yes. Okay. The next thing we're going to discuss is what a counterexample is. So a counterexample is when we have a specific case for when the conjecture is false. Okay, that's when we want to like prove our conjecture wrong, almost like devil's advocate, if you've heard of that terminology before. So to prove a conjecture true, you have to show that it is true for all cases. That's the other blank we're filling into our notes for today. And then to prove a conjecture is false, however, you only need to find one counterexample. So it's kind of like in real life. It's really easy to prove someone wrong because all you have to find is one way that it disproves what they're saying. But if you want to prove something that's true, you have to give all the evidence that's true in court, is true when lawyers try to make their case and fight the cases for their clients. Okay? So let's continue going on and talk about how can we make a conjecture based on the following statements. It says a student makes the following conjecture about the sum of two numbers. Find a counterexample to disprove the student's conjecture. So we're going to try to disprove what they're saying. The sum of two numbers is always more than the greater number. Well, that's true when we have two positives. 2 plus 5 is equal to 7, okay? But what happens if we add two negatives, like -2 plus -3 is equal to -5? Is -5 greater than -2? No. So this is how we create that false counterexample. Okay. Number 4, make and test a conjecture about the sign of the product of any three negative numbers. So any three negative numbers, let's say, make it easy. -1 times -2 times -3. That is going to give me -6. Okay. There I've created a negative. How about -5 times -2 times -4? That's going to give me -40. Okay. So when I have three negative numbers, my answer is negative. Okay. So that would be making and testing the conjecture. How about this one? Make and test a conjecture about the sum of any 5 consecutive integers. So consecutive integers would just be positive or negative whole numbers. So let's maybe start with just this one. 2, 3, 4, 5, 6. If we added those together, it gives me 20. Cool. Let's do another one. Negatives. -2 plus -1 plus 0 plus 1 plus 2. Okay, that's going to give me 0. The one thing I want to maybe think about is if I focus on the middle number, how does 4 maybe relate to 20? 4 times 5, right? How does 0 relate to 0? 0 times 5. So we can say the sum of 5 consecutive integers is 5 times the middle number. Okay. For number 6, find a counterexample to show the conjecture is false. And it says the value of x squared is always greater than the value of x. Okay. This is going to be true for a lot of cases, like 2 squared is equal to 4, and 4 is greater than 2. But it's only false for one, or one that I'm thinking of. If x is equal to 1, then x squared would look like 1 squared, which is equal to 1. And 1 is not greater than 1, so that is false. So there is my counter example for that one. Or how about this one? The sum of two numbers is always greater than their difference. If I found the sum of two numbers is always greater than their difference, so let's pretend I'm doing 5 plus 3. 5 plus 3 is 8. There's my sum of two numbers. Is that sum greater than their difference? 5 minus 3. Well, their difference is 2. That checks out. That's true. But I need a false statement. So maybe I try to put them in negative format. Negative, because when you compare negatives, it's always opposite day, right? Let's try -5 plus -3. That's -8. And then the difference of -5 and -3 is equal to -2. Here is where we can maybe discuss the sum is not greater than their difference. So here's where we can make it say false, because -8 is not larger than -2. That is false. Okay. going on, now we're going to start to get into deductive reasoning. So deductive reasoning is using facts, definitions, properties, laws of logic to form arguments. This is different than inductive reasoning, and we're going to talk about the differences here in a second. Inductive reasoning is going to use specific examples and patterns to form a conjecture. So this is how we're going to see this. We have two different laws we're going to be working with. The law of detachment says if the hypothesis is true, then the conclusion is also true. Okay, and we'll work on what are those examples here below. The law of syllogism, though, is a little bit different. If you have a hypothesis and you are able to conclude Q, then that means you can make a hypothesis from Q and then create another conclusion. Okay, that only happens though if those two statements are going to be true. And again, we'll talk about an example in a minute. If the hypothesis, so going from there, you can go back and then use the original hypothesis P, and then can make that conclusion all the way down to R. So, for example, if you make A's and B's on your report card, you get $20. And if you get $20, you can go buy a new shirt. So the law of syllogism would be kind of like the domino effect. If I make A's and B's on my report card, I can go buy a new shirt, and you can skip the whole middleman of then I get $20, so now I can go buy my shirt. Okay, so detachment is true no matter what. You don't have to prove it with a middle conclusion. Syllogism is proving it with a middle conclusion, or trying to like bridge the gap between hypothesis P and conclusion R. Okay, so let's talk about what we can do here. It says for the first one, if two segments have the same length, then they are congruent. You know that BC is equal to XY. So using the law of detachment, what statement can you make? Well, BC equals XY, so that means BC is congruent to XY. This is the law of detachment, because if you go back up here and reread that definition, this is a true conditional statement. The conclusion will also have to be true. Those are just straight hard facts, okay? Let's talk about this one. If possible, use the law of syllogism to write a new conditional statement that follows from the pair of true statements. So all of these statements are true. If x squared is greater than 25, then x squared would have to be greater than 20. So if x is greater than 5, then x squared is greater than 25. How we'd be able to make that connection is you would start small with this all is possible if we can make x be greater than 5. So we would start our law of syllogism like this. If x is greater than 5, then we can for sure make x squared greater than 20. We already know 5 times 5 is 25, and so anything greater than that will give us 25. But to even go further than that, we can say that if x is greater than 5, then we can for sure say x squared is greater than 20. How about this one, though? If a polygon is regular, then all angles in the interior of the polygon are congruent. If a polygon is regular, then all its sides are congruent. Okay? For this sake of reasons, we will not be able to use the law of syllogism. So not possible. Okay? And the reason is because we can't always tell. You can't always prove that unless you give more information that all angles are congruent from there, okay? And it didn't go on to say that they're making that connection piece. So the shared piece of this is if, so their sharing is both of the if portion. Okay. And to try to reiterate the second example, if a polygon is regular, then all its sides are congruent. And if a polygon is regular, then all interiors are the same. We're not using the law of syllogism here because we would have to write a completely new statement to make that work. So neither of those conclusions is the same as the other statement's hypothesis. So they're not bridging the gap there. Okay. Here we go. Let's try this example. What conclusion can you make about the product of an even integer and any other integer. So the product meaning multiply, so you take an even integer and you multiply it with something else. 2 times 3 equals 6. Cool. How about negative 2 times 5? That's negative 10. 4 times negative 8, negative 32. Negative 4 times negative 8, positive 32. Okay? What we're seeing happen here is all of these numbers are equal to an even number. So we can say the product of an even integer and any other is also an even integer. Integer. Cool. Next, decide whether inductive reasoning or deductive reasoning was used to reach the conclusion, and then explain your reasoning. So each time Monica kicks the ball up in the air, it returns to the ground. So the next time Monica kicks the ball up in the air, it will return to the ground. This one is solely based on inductive because a pattern was used to reach a conclusion. This is a lot of the times what you do in science. Like when you do labs in science, you're making an inductive conclusion. Okay? All reptiles are cold-blooded. Parrots are not cold-blooded. Sue's pet parrot is not a reptile. This one we would consider deductive because there's not a specific pattern that's happening because what we're doing is we're use facts about animals to reach a conclusion. To reach a conclusion. Okay, so when we've got the facts, we can use deductive. When we don't have facts and instead we have a pattern, that is where we have inductive. How about this one? If 90 degrees is less than the measure of angle R, which is less than 180, then angle R is obtuse. The measure of R is 155 degrees. So using the law of detachment, which means we want to make sure we're using known facts, what statement can you make? The statement we can make is since R is 155, it's in between those two numbers. So we can say that angle R is obtuse. Okay. Using the law of syllogism, so here it is where we're going to connect from one part, the very beginning of our statement, hypothesis, all the way down to our conclusion. That follows the pair of the true statements. If you get an A on your math test, then you can go to the movies. If you go to the movies, then you can watch your favorite actor. So the law of syllogism would state, if you get an A on your math test, okay, that's your first hypothesis. The first conclusion is movies, but we want to pair it up with the last conclusion. Then you can watch your favorite actor. Okay, so again, that connects from the first statement to the very last conclusion. Okay, number 10, use inductive reasoning to make a conjecture about the sum of a number and itself. Then use a deductive reasoning to show that the conjecture is true. So if you take the sum of a number in itself, like 3 plus 3 is equal to 6, that is 3 doubled to get 6. Or 5 plus 5 is equal to 10, that is 5 doubled to get 10. So what we can say is the sum of a number and itself is twice the number. We can always prove that with, let's say, x plus x equals 2x. Okay? Finally, number 11, decide whether inductive reasoning or deductive reasoning is used to reach the conclusion. All multiples of 8 are divisible by 4. Understand that this is a fact, so that should help you decide if it's inductive or deductive. 64 is a multiple of 8, so 64 is divisible by 4. Going back here one more time to the parrot example, we were able to say this is deductive because we used facts about the animals, and right now we're using facts about math. So this is deductive. There's no pattern here. It's based on math facts because it's using law of detachment to reach conclusion. Okay? All that means is there are facts, not patterns. Okay? That is going to conclude our lesson on 2.2, inductive and deductive reasoning. Thanks so much for tuning in.